I never. Never. But it's my life. I forgot that book for you. God bless me. I knew I was doing something. I'll write it in my agenda right now. I'm going to bring it to you. Come back with it. You sound better. Are you needing a break? After you feel better?
Go run every morning. Go run and oats. Make their food.
Yeah. Me too.
Did you?
I shared it after this one. I like the whole stuff.
Same. I'm just finishing up my colors and then I'm just
I heard someone say that not Suki, but it says nowhere on the map it's Suki.
They have.
and he would say, yeah.
Okay. They.
I think I have like, I have like 1% make comments, and then I
Oh, I'm not here.
Right. I'm finishing up my comments on one person. How much of the God in your penis?
Are you going working spots?
There's one other girl in here.
Okay. Yeah. Are you?
Step out. No, I was just trying to. I like that. Just don't eat on it. Because that
Oh, that's disrespectful.
Yeah, I'm used to it because high school, my pocket.
So I think that's ridiculous. It's evolving.
Our kids not even allowed to have, they're supposed to be locked in the altar.
I mean, that's not safe with all the school food and stuff. You know, it doesn't happen. If they have it, I mean, make it a backpack rule, but let them keep it. Or, what they were starting to do in my school before I graduated was those thumb cubbies on the walls. You can hand with your thumb.
Yeah.
That way, right there. Because I just think that's great.
Yeah. The problem with at my school was that a lot of people like did like this and just like.
Well, that's everything for everyone.
I never did that.
Okay, I didn't know.
I was angry. I tried it.
That's why you got the drinking.
Sometimes I zoom out. And then,
I haven't looked. Do you not have a Blackboard login?
No, I do. I just don't know how to do it.
Show them my grades.
If you can get the Blackboard, do you not know how to get the Blackboard? Is that what you do? There's an app too.
Okay, I know how to get on there because I like try to get my homework on there for my online classes, but I don't know how to check my grades.
Okay. Well, sometimes if you just look,
Get on there.
Show me.
That's better. You can get on that. This is there.
There's an app for it.
Yeah. What is it? You know what it's called? But just put Blackboard in and see if it gets that. I'm on my computer so much I don't know. Where you only have a couple.
I try to stay off.
when you first go on the
It's
Blackboard,
fluid.
it's going to be right here, and it'll say my grades.
Alright. My computer science teacher posted a link to the grades page. For all my other classes.
No, you just, there's a spot, you just have to mess with it. And when you open it up on a computer, you can, it's you see it.
I've never used it.
Well, it's like a universal policy. Be good to mess with it. I find Google Drive, honestly, to be still helpful. And also, I used to I think when you get on the app, you just well, I'm on my computer, so the phone I used to have wasn't supported. I got this one. See, you're talking to the app.
Bailey told me she heard that. And it was like, no.
It's straight up listeners, so
I'm certified. So I'm pretty excited. I was supposed to drop in calculus that one time and really put off because if not, I would take it.
I gotta get an A in this class now to raise my GPA. Because I have like a, I think I actually have like a 3 side. Because where I had to drop out.
I did, in geometry, so hey, it's pretty nice to have some.
I tried to take it earlier than this.
Scanned everything.
The teacher wasn't. He, just had to take Sal on,
I was trying to do it, I was like,
You guys.
she knows that she just makes sense. See what she will actually.
well, man, Bonnie Mae, we did an extra class.
But middle school. Well, but I am,
Course description.
I'd be interested in that.
You guys had like these like
I think the only offer was,
No, when I took site, it was in that like evening, and I had it actually in this room. She called her name, but then her husband was like class over there at the same time. Which one?
I know, even when I left, you said, I did that like right.
Just as long as you're, and as far as like the function, but that's just the way you got to do something. That's the thing.
As long as it doesn't get worse than that.
No, I mean, I took AP and stuff off the school, and I don't think it works. I just feel like you have to learn keep yourself scheduled, making the time to do things that don't get out for you. And I feel like that's what you should probably limit that more so than
Crazy technique.
because there's every good college student almost has some sort of violent or
She didn't put on,
So on my outbreak, is it just because like all the grades aren't in yet?
oh, yeah.
You can spin your. Is it this already? What were you working? Yeah. Allie, Michael, and I still can. I do other class at. But every time we got out of class. Yeah. That was annoying. We got out at like 8:20. Yeah.
Okay, let's check the attendance. Megan? Here. Austin, not here. Elsa? Here. Allison? Here. Katie? Here. Jesse? Here. Leah? Here. Catherine? Catherine? Here. Okay. Madison? Madison? Curtis?
Here.
John?
Here.
Okay, did you sign up for class late?
Probably, yeah.
Okay, because I guess I didn't have you on the first day of my attendance sheet.
Oh, okay.
And the other thing is, looks like your submission to Blackboard was not successful.
Really?
What I see is like sort of in the process. And so you can either try to resubmit your homework 1 and homework 2, or you can email them to me.
Okay.
Okay.
Thank you.
All right. And so today I will post a practice exam on Blackboard under this week. And for the students from this campus, they get a hard copy, but for the other campuses, you have to download them, or you print them out. And if you don't have a printer, if you just want to handwrite your solutions, that's fine. But if you can also print out and work on the practice exam. So it looks like this. Is that working? that's not work.
I feel like maybe the first one.
I don't think it does.
It's almost like here.
It's not showing the camera. Oh, did I not turn this?
Oh, yeah.
Oh, I'm sorry. Okay, yeah, this. Okay, so this is the first exam, the practice exam. The first, you can use this as a study guide to prepare for the first test. And the first exam will be very similar to this. It has about 4 pages. And some of the problems we're going to cover this week and next week. So like the problems on page 4, you won't be able to do like special last 2. I think you're going to be able to do up to probably after today's class, you may be able to do the problems up to number 13. Okay. But it's due on September 23rd. So you have about 2 weeks to do this. So today, first I'm going to try to, the homework doesn't seem to have much problem. I guess one of the problems I probably typed it wrong and different from the textbook. So if you did the problem on the textbook, that's fine. Or you did the problem on the one I post on Blackboard, that's also fine. I consider both as correct. So we are going to, first I'm going to finish, the topic chapter 2 today. And if I have time, I may go back to the homework and talk about the homework. Okay, so we covered 2.1 last time. And let's see, have I finished that? Okay, so we were talking about the translate from the sentences to symbols, from the symbols to sentences. This is what we had at the end of last class. Well, so if you're given a formal language, like symbolic form, you need to understand what this means. So in the sentence corresponding to that would be the square of any real number, or every real number is non-negative, or is greater than, or equal to 0. And what if we are given an English sentence in formal language? We want to translate it to symbolic form or formal language. You will use the symbol for the word of. You can read it up. For any triangle T, T has 3 sides. So you have to kind of introduce a variable to represent any triangle T, or any dot D. Now we also looked at an example of if we have if-then. Yes. Okay. So another example we looked at was we are combining the universal statement for any and if-then statement, which is conditional statement. So that kind of thing we have in it's a property we have in mathematics. All kinds of property a lot of times are described in this way: if something something, then something something. But it works for a lot of numbers, any real number. So it says if a real number is integer, this real number, it didn't say which real number, so it's any real number, or you can say all real numbers. as long as it's integer, then it is a rational number. So we can rewrite it in this form for any of something. So let me maybe do this for any kind of x, for any real number x. If something about x is true, then something else about x is true. So it's sort of like in this format. Now we can look at another one for existential statements. We want to example 4. We know a prime number is, what kind of numbers are prime numbers? Right, yes. Okay, so think about all the prime numbers we have. We know that, look at this statement. There is a integer that is both prime and even. Is this a true statement? Yes, right? What integer is that? 2, right? Okay, so this is the informal language. We wanted you to rewrite it in symbolic form. So there is, we use the symbol, kind of like a backwards E, and there is a integer. So you have to, for this integer, introduce a variable for that. Usually, I guess for integers, you can use the letter n. For real numbers, we like to use the letter x, but really it's up to you, whatever letter you want to use. So we're going to call this integer n, the letter n. So there exists integer n such that n is prime and n is even. The format of this sentence is there exists something such that something. There exists something about n, the letter n, such that something else about n is true. Okay, so that's the this type of question, converting between formal and informal. And now we are going to look at section 2.2. Let's take a second to look at the homework 2.1. We did cover, last time I gave you examples similar to number 2. Oh, I'm sorry, not number 2, number 3. So number 2, when you look at number 2, they gave you those statements, but these statements are either universal statements, I guess both of them are universal statements, and you want to determine whether the statement is true or false. This asks you to justify your answers as best as you can. So if a statement is true, I don't need you to justify it. It's going to be very hard for us to do right now. But if it's false, I do want you to justify that, because how do you justify if it's false? So when I say all school buses are yellow, and if you think this statement is false, how would you justify your answer? Say, why is it false? What do you have to do? How do you show me my statement is false? What will you do? So I say, I have a statement. I say, I claim all school buses are yellow, but you think that's false. So that's your conclusion, it's false. But you need to justify it. Why do you think my statement is false? How would you do it? Yes?
There
Someone?
exists.
Huh? Yes?
There exists a white school bus.
Okay, yes, that's right. So there is a white school bus. All you have to do is to show me you can find one, at least one, or maybe many, but at least one that is not yellow. Either white, say, okay, here is a school bus that's white. And that proves that I'm wrong, right? The statement is false. Is that correct? Okay, so for universal statements, whenever you see for any or all, every integer or all real numbers, they're saying that these statements are true for every single one. Just like when I say all school buses is yellow, I mean every single school bus in the whole world is yellow. And as long as you find one that is not yellow, you prove that I'm wrong, okay? So to prove something is wrong, it's very easy. But to prove something is true, it's not easy, okay? If you want to prove every integer is a real number, it's not going to. Or if I want to prove, I say, I insist that I am true. I will have to prove you, I have to find every school bus in the whole world and show you every single one is yellow, right? But that's not going to be easy to do because there are, millions or even more than probably. A lot of times when we talk about integers, there are infinite many integers. You're not going to be able to take every single integer and show me that's integer, every single number. Just like it's going to be very difficult for me to show every school bus is yellow because I have to literally find out every single school bus and show you it's yellow, okay? But so this is something else we're going to discuss next week, how to do the proofs. How would you prove any even number squared is still even, okay? You cannot just say, well, look, I give you a few examples. 2 squared is 4. 4 squared is 16. 8 squared is 64. They're all even. That's not a proof because you only showed a few cases. We want you to show every single even number. And how many even numbers do we have? Infinitely many. You cannot sit down there and list every single even number and show me, and square them and show me they are even. There's no end of it, right? So that won't be counted as a proof. But we will have a way to do. So that's the topic of next week. Okay, so that's first. Number 2, you if you believe it is true, you don't have to justify it. If you believe it is false, give me one counter example. So just like the white school bus you found it's a counter example to my statement. Okay, now number 3, we did cover that last week. So follow example there. By the way, if you have to miss a class or something, you can email me and I can send you a link to the class video. So all the class videos are recorded, so I can you can catch up that way. And also I made videos and about every single homework problem posted on Blackboard. So if you have trouble doing any of them, you can also find videos on Blackboard. Now, let's see. So number 7, we didn't do exactly the same type of questions, but it's kind of similar to number 3, as long as you understand what the truth set means. So like number part B, it says the sentence we call it a predicate, but it's just like a sentence with a variable. So 6 divided by d is an integer, and the domain means what kind of numbers we take for the variable d. Z plus, which means all positive integers. So when you consider whether this sentence is true or false, you just need to consider those positive integers. You don't have to worry about negative or 0, okay? So they specify the domain. Just like functions, you can only plug in numbers in the domain, not numbers not in the domain. But you may say, well, we can plug the negative numbers, 6 divided by negative 3. Yes, you can, but we don't want you to do that. We just need you to do positive integers. Okay, so the domain is specified here. So what you have to do is to find what kind of integers, positive integers for d, such that 6 over d is a integer. That would be called a truth statement, right? So if 6 over d, when you plug a number for d, you do get an integer, that's true. That makes the predicate true. That number should be in the truth set. Otherwise, it's not. So similarly, you can do part C. Part C might take a little bit of time if you learning algebra, how to solve for x, you can. If not, you just have to do what we did in class. Pick numbers, plug it in. When you pick numbers, you could draw a number line and pick different numbers. Pick some positive ones, some negative ones, pick 0. And when you pick, also try to, for positive numbers, you can also pick like numbers greater than 1, numbers less than 1, and so on. Okay, so number 10 and 12, it's similar. They specifically tell us these statements are false. You just need to find a counterexample. So it's like when I say all school buses are yellow. So they're saying any integer is A. For any integer A, when you subtract 1 from this integer and divide by that integer, you're not going to get an integer because it doesn't look like a fraction. Well, but we know some fractions could be an integer, right? Like 2 over 1 is still going to be an integer. 6 over 3 is still going to be an integer. So this apparently is a false. But you need to find a counterexample. Excuse me. So when we say counterexample, it's you found an integer for A, and then you plug it in. You get it. A minus 1 over A, you get an integer. Okay, they're saying it's not going to be an integer, but you found something that's going to make it an integer. That would be called a counterexample. Okay, so always remember the example I say when I say all school buses are yellow. If you found a white one, that's a counterexample to my statement. So white school bus is not yellow, so that's like that's a example, counterexample. So similarly, you can do number 12. Number 16, I gave you examples like the one I just went over. And number 17 is also what we just did. Okay, all right, so hopefully that will help you do the homework question. If you still have trouble, send me an email or find the videos on Blackboard, or you can ask me next Monday. Now we're going to move on to 2.2. We introduced a new type of statement called a quantifier statement. Like I said, a lot of properties in number theory or discrete mathematics or other subjects are written in this form. And so we are going to first look at the negation of these statements. 2.2. Still going to be talking about quantifier statements. I guess we can this quantifier statements. Part 2. Oh,
Can you change this?
yes, thanks. Quantifier statements. Part 2. The 2.1 is part 1. We introduced. We looked at the examples for universal or existential statements. So now we're going to do negation. How do we find the negation of those statements? All right, so think about how we did negation. When I say, if I say I am a professor, and when I negate this sentence statement, I just say I am not a professor. So I would add the word not in the sentence. That would make it a negation. But with universal quantifier statements, we got to be a little bit careful. So when I give you, say, look at the example we had, all school buses are yellow. How would you negate that? All school buses are yellow. What will be the negation of this quantifier statement?
Could it be some school buses are yellow? Or not all school buses are yellow?
Okay. So, any other answer? Any different answers? I didn't hear anybody say all school buses are not yellow. But in the past, I always had a student who say that. Well, I am a professor, so when you negate it, you just say I am not a professor, right? So you put a not right after that be verb there. So can we do that for this one? No, we can't, okay? So all school bus is yellow, when you add a not, you gotta be very careful. Don't add a not right after R. So you cannot say all school. So a wrong answer would be all school buses are not yellow. All school buses are not yellow. This will be wrong. The correct answer, who answered the question? What's your name?
Leah.
Leah? Okay. So Leah said, she gave us two answers. The second one she put a not in front of all. Not all school buses are yellow. This will be a correct answer. Not all school buses are yellow. She also gave us a different answer, which is also correct. Some school buses are not yellow. Some school buses are not yellow. Okay. Well, you could put not in front of all, but you could change all to some and add a not after R. You cannot directly add a not in the sentence, but after you change the word all to some, yes, you can add a not. Okay. And look at these two answers she gave us. They are equivalent, right? When you say not all school buses yellow, you mean some of them are not yellow. That's the same thing. But you look at the wrong answer and the correct answer. Are they talking about the same thing? If you say some school buses are yellow, are not yellow, and all school buses are not yellow, are they the same thing? No. When you say some school buses are not yellow, which means some may still be yellow, right? But when you say all school buses are not yellow, not a single one is yellow, correct? Okay, so be careful. The negation will not be that one. This will be wrong. The correct answer will just say some school buses are not yellow. Okay, so when I make this statement, if I say all school buses are yellow, you will say that when you say it's false, because you can find some school buses, or even one, that's fine, some school buses, you don't need to show me every single one is not yellow, okay? All right, that's the negation for this statement, because there's a word all in here. That's called a universal statement. And we're going to summarize into like a formula. See how we do that. But when you look at it, it's kind of, you already see the pattern. When you have a universal statement, how would you change it? How do you get a negation? All will be changed to there is, right? Some means there is a school bus. And you negate that. R becomes R not. So that's the formula, where you can call it a pattern. I'm going to write it, summarize here for you. So the negation, the first example is for a universal statement. The negation, maybe I call it, let's see, negation of a universal statement. We are given a universal statement. The universal statement, all school buses yellow, rewrite it will be for any school bus, change it to formal language with like symbolic form. That would be easier for us to write down the formula. So for any school bus X is yellow. So that's my original statement in symbolic form. In general, any universal statement will look like this. For any something X, either school bus, either dog, or logician, whatever, or a real number, or integer. So it's going to look like this, a universal statement. For any X in somewhere, for any X, the textbook used the in D. D is the domain for the X. But this part, usually, if you don't want to worry too much about it, it's fine. So the X is something. So there is always a statement about X. X is yellow, or X is lazy as a logician, or X is something. So we call the statement Q of X. So in this case, in my example, D means all school buses. The domain for this X is all school buses. So for any school bus X, Q of X is a statement about this school bus X. So Q of X means X is yellow. The school bus X is yellow. So any kind of universal statement, you can always describe it this way. And when we do negation, what do we get? Remember what we did? For any changes to there is, right? So there exists. When you do, there exists a school bus. There exists a school bus such that there exists a school bus X. School bus X. Such that X is not yellow. X is not yellow. And if we compare the symbolic form, for any becomes there exists. X is yellow because X is not yellow. So the formula will look like this. Can you see the bottom? Yes? Okay. So there exists X in the domain such that the negation of that statement about X is true. So you negate that. So I'm going to highlight the changes we made when we do negation. For any will become there exists. And Q of X, well, you're going to have to do negation right here. Okay. There exists. And all right, we can do an example. So the statements I'm going to give you here may not be true, so they could be false. For any prime numbers, P is odd. All we want you to do is to do a negation. What's the negation of this? Yes, so there, you can use your common sense to do the negation, or you could use the formula that we just gave you. And when you have a universal statement, change for any to there exists. This is changing to there exists. Such that, for existential statements, we usually like to add a word, such that. And you got to negate the statement about P. P is odd, we negate it. It becomes P is not odd. Okay. Well, which is, we know, it's number 2 is a prime number that is not odd. Okay, that's for a universal statement. Now we're going to look at an existential statement. And it's kind of...
I have a question, I'm sorry. In that example we just did, is P is not odd. Is that Q of X? Or would that be like the negation of Q of X?
This whole thing?
Yeah.
So Q of X will be the statement, right? That's Q. Q, in fact, we didn't use X, we used the letter P here. So I missed the letter P there. So it exists the prime number P. And so that's Q of P. Now we got to negate that. How do we negate this statement? Just add an odd, not in there, right? The P is odd. That's Q of P. I know in my formula I use the variable X. That's the common one. But sometimes they may not use X. In this case, they use the P. So this statement would be a statement about this capital letter Q is a statement about this number P. P is the variable. Did I answer your question?
Yeah.
Okay. Now what if we have existential? Any other question? All right. So what if we have existential statement? For example, if I say some school buses are yellow, we can look at. So this will be example 2. Example 3. When I say some school buses are yellow, how do we, apparently this is an existential statement because Just like saying there is a school bus that is yellow. Now, how do we negate that? What would be the negation of this sentence? Some school buses are yellow. Negate that. All school buses are not yellow. All school buses are not yellow. Any different answer? Do you all agree? Yeah. Okay. So when I say there's some school, maybe at least one. It's kind of like saying at least one school bus that is yellow. When you want to negate me, you will have to say not a single one, which means all school buses are not yellow. Right? Okay. Not a single one is yellow, which means all school buses are not yellow. Look, what have changed? Highlight the changes. What have changed? Some means they exist. Now in negation it's for any. All means for any. Now in the original statement it says school buses are yellow, and now it's changed to are not yellow, which is the negation, right, of that second part. So the formula for existential statement from this example, negation of an existential statement, will be changing there exists to for any. Negate that statement about whatever the variable is. So let's look at the statement. Originally we said there exists a school bus X. D means the domain, all the school buses for X. So there exists a school bus X such that X is yellow. We're going to use Q of X to describe that statement. Because we may not always talk about school buses. We may talk about such that the logician is lazy, such that 6 over D is an integer, something. Whatever that statement about X is, we call it Q of X. Again, it may not always be the variable X, could be any other letter. We're going to do negation. We're going to get, from the example you can see, there exists, we're going to change it to for any. For any school bus X. X is not yellow, which means you're doing negation of the statement about X. Because Q of X originally means a school bus X is yellow. Now, you're saying school bus is not yellow, so you do negation of that. I like that. All right, so we can look at example. There exists a triangle. Use the formula. There exists a triangle T such that the sum of the angles of T equals 200 degrees. We know it's not 200 degrees, it should be 360, right? So this is a false statement. Now we want to negate this. Okay. Any volunteer? What would be the negation? Curtis, do you want to try?
Like, do you just want the sentence, or do you want all the symbols?
No, you don't have to use symbols. Just say the sentence.
All triangles T.
Okay. All triangles T. We're gonna follow this way for any triangle T. All triangles. We can just say we call for any triangle T. And what about the triangle T?
The sum of the angles will not equal 200.
Yes. So the sum of the angles of T is not equal to, let does not equal 200 degrees. Okay. So look at the changes we made. Just like the formula, there exists, we change it to for any. Equals, we change it to does not equal. So this whole statement right here, the sum of all angles equals 200, that's what we call a Q statement. But variable here, we use the T, so it's like Q of T. But when you do negation, we got to negate that. Negation of Q of T, you add a not in the original statement. Okay, questions? Well, next we're going to combine conditional statement with these statements, quantify the statements, and we're going to do negation. But before that, let's review the negation of a conditional statement. That's been, I guess, a while. It's about 2 weeks ago. So recall what we learned. If I have a conditional statement, if P then Q, and what would be the negation? I guess we also did it last week, though. In the homework, we had those. Does anybody remember?
P and not Q.
Very good. P and not Q. Okay, so it says, again, use a really life example. If I get 93 or higher, I'll get A. A negation would be I get 93 and higher, and I don't have A. So that would be the negation for conditional statement. So now let's put them together. Let's add the universal statement in there. When we do that, we not only you have to use this formula we learned before. We call it logic, common sense logic, but also you got to use what we just learned, the negation of a quantifier statement. So let's look at example 5. If in if a real number is greater than 2, then its square is greater than 4. That is a true statement. I don't think we're asking to determine whether it's true or false, but we want you to do negation here. Okay, this just looks like a conditional statement. But before, when we do the statement, we always have a specific number. Let's say if 5 is greater than 2, then 5 squared is greater than 4. But now we're saying, well, you could have if 6 is greater than 2, then 6 squared is greater than 4. If 2.5 is greater than 2, then 2.5 squared should be greater than 4. So we always have this, we had a specific number given. But in this case, it says, it works out for any number, any real number. It doesn't have to be 5 or 6 or 2.5. It could be any real number. As long as this real number is greater than 2, its square should be greater than 4. Okay, so this part right here, it's for any real number. So that's the universal statement we have been talking about. There's also if-then. We know that's a conditional statement because not every, if I get rid of that, not every real number squared is greater than 4. Like 1 squared is not greater than 4. But we also have to have another condition. It's not any real number. It's a real number that is greater than 2. Okay. All right. So can you just use common sense or logic? What is the negation of this? You can also use the formula we talked about. So we are saying if a real number is greater than 2, then its square is greater than 4. What would be the negation? Remember?
A real
Yes.
number is greater than 2, and its square is less than 4?
Less than or equal to, right?
Yeah.
Opposite, the negation of greater than will be less than or equal to. That would be correct. So that's what we just talked about, the reviewed, the negation of conditional statement. You keep the hypothesis. You change the conditional statement to and you got to negate the conclusion. So that's what we can do. But later, I will use a different way. So if you can do that, that's fine. So it says a real number is greater than or equal to greater than 2. I'm going to just, let's use words for now. It's greater than 2. And, don't forget the word and. Its square is not, you can just say it's not. But if you want to change it to less than or equal to, that's fine. So it's not greater than 4. So that's the negation of conditional statement. It doesn't, well, okay. Here, actually, a real number here, there's a little bit of problem here. Do you mean any real number greater than 2, or just some real numbers greater than 2? So are you saying any real number, if it's greater than 2, is greater than 2, and its square is not greater than 4? So when we say a real number here, there is a little bit of confusion, not very clear. In fact, there should be adding a word. There is a real number that is greater than 2, and its square is not greater than 4. Okay, we're not saying every single real number greater than 2, and its square is not greater than 4. Okay. Now we are going to use symbols. So if this confuses you, using symbols will be symbolic form and applying the formula that will make the problem. Where you don't really have to, you can just follow a formula to do this. The original problem, I'm going to rewrite it in the symbolic form. So first, to change the original statement in the symbolic form of original statement. Does anybody know how to do that? So I think we just had an example for that last time. So it's sort of like this. If a real number is integer, then it is a rational number, so you want to change it to this format. For any something, if something, then something. So how would you do that? Anybody that wants to try? No? This is what I need for any something that x. If something, then something. Something implies something.
Is this the symbolic form for the negation of the original statement?
Original, of the original. Because I'm trying to apply the formulas we just talked about, like, conditional statement, this is the formula to do negation. Universal statement, this is the formula to do negation. So in order to use the formula, you have to have them in that symbolic form. The original statement here. Who asked the question?
Would you put it as x belongs to R and
Yes.
then greater than 2? Or would you have to put x greater than 2?
Yes, x. You got yes, specify. But there is a word if. If x is greater than 2, then what? X squared is greater than 4. And now I don't have any English words in here, right? So it's purely symbols. Okay, you got it right? Yes. Okay, good. All right. So any kind of statement like this, you can always change it into symbols. Now we are ready to use the formulas. The whole thing here, I'm going to do the negation. Also, we have symbols. think when you do the homework, you could, the homework problems, I think all of them are in this symbolic form already, and it's not the sentence, so you don't have to change that, it's already in this form. So then when you do negation, okay, let's put negation on for x equals r, x greater than 2 implies x squared greater than 4. So we are going to first, it's a universal statement. And how do we do the, so this is like the for x part, and this whole thing, if then part, we consider it as p of x. So for any real number x, something about x is true. What about x is true? If x is greater than 2, then x squared is greater than 4. That's a statement about x. Although this statement is also a conditional statement. This statement, it also has 2 statements there. But we still can consider it as one statement. But when we do negation of universal statement, what do we change? Yes, this will be changed to there exists a real number x such that we're supposed to negate that part, right? So I'm going to slow down here, but later you don't have to show me this step. You can just write down the answer directly. So following the formula of universal, the negation of universal statement, you change it for any 2 that exist. You got to negate whatever that statement about x is. So you put negation in front of that p of x. That's our p of x. But look at the p of x. P of x is not just a simple statement. It's a conditional statement. And what is the negation of a conditional statement? We got to continue to look at the next step out. So the first part we can copy it. There exists a real number x such that
X is greater than 2. And
and
x squared is not greater than 4.
is not greater than 4. Right. Because that part says whenever you have conditional statement, you keep the hypothesis, change the conditions to and, conditional statement to and, change this implication to and negate the conclusion. So we're doing 2 steps. But if you understand this, you don't have to do 2 steps. You can just do 1 step. All right, so when I get this question for any becomes there exists, I got to negate this part. How do I negate that part? Because it's conditional. We keep the hypothesis, change this to and negate the last part. So we have another formula when you have everything combined.
Should we write out the word and, or do you want us to use the symbol in that last part?
For this one, you don't have to use words because the words and the symbols, they're exactly the same thing. Okay, previously, in one of the homework questions, I know some, like they had this statement, they ask you if something, then something. And they ask you to do control positive or inverse. You do have to write down the sentence because this P could be anything. This Q could be anything, right? But over here, it's very clear what P is, what Q is. So you don't have to use words anymore. We're not just using a regular P of X. But again, you cannot just give me this formula. Say, okay, it's going to be this formula. And you have to plug in what your Q of X is, what your domain is. But not this formula. You have to write out. So what is that P of X? The P of X is x is greater than 2, then x squared is greater than 4. So as long as you have this, that's the same as the sentences. If you say I prefer sentences, that's fine. I think symbols might be easier. Okay, so take a look at this kind of statement. What would be the negation? We can summarize it in the formula. So look at this example, what we did. So when you have a negation of, for any x in D, P of x implies Q of x. Use lowercase. So when we do negation of a combination of universal and conditional statement, what do we get? For any becomes exists such that, and negate this part. P of x and negation Q of x. The symbol, I guess I can use the other. Well, let's just keep the word there. And okay, so look, this formula comes from the universal statement negation formula and conditional statement formula. So first we apply this for any change for any Q that exists. Next we gotta negate that part. So the capital letter Q of x, the statement over here we got a complicated statement, conditional statement. So when I try to negate this whole thing, I gotta use another formula, which is keeping the hypothesis, change implication to n, negate the conclusion. Okay. All right, and you don't really have to spend time trying to memorize this formula, but this kind of summarize, give you a quick tip to do this if you cannot really do it by common sense. So change for any Q that exists, keep this, negate that, and change this to n. So do a few changes. All right, now next example. We can, for the statements here, we also need another type of question is, okay, all right, so I think that would be, there are some more stuff talked about in the textbook, like how we do contrapositive, how we do converse and inverse. And that would be the same as before. So if you look at this statement here, this is a kind of conditional statement. We can always do contrapositive, converse, and inverse. In the homework, I think maybe there's one or two students who don't get the definition. The definition is something you have to memorize. Conditional statement, P implies Q. That's the original conditional statement. Conditional, and let's review that. What is converse? Now, what would be the converse of this statement?
Q then P.
Q implies P. You switch hypothesis and conclusion. You don't do any other change. And what would be the inverse?
Not either not Q.
You negate both hypothesis and conclusion. Contrapositive, that's the one we gotta do both. Not only you gotta negate, but also switch. So you got negation of Q implies negation of P. So you kind of have to memorize that. Applying this, you can do the same thing. You can do the contrapositive. So let's first do the converse. I think I don't need to write this down. Just quickly, somebody can. Yes, Katie, can you tell us what the converse is? The statement right here.
Would it be, was converse the Q
Switching, yeah, you're switching the conclusion and hypothesis.
So would it be then if it's square is greater than 4, then a real number is greater than 2?
Yeah, but you might have to do a little bit of change because you start with this one first, right? You gotta probably what's that it's. So maybe you should say if a real number squared, if the square of a real number is move the real number to there. Okay, so if so we know what it means. If the square of a real number is greater than 4, then this real number is greater than 4. if you add x, it will make it easier. If the square of a real number x is greater than 4, then x is greater than 4, greater than 2. All right, so that's the converse, and what would be the inverse? Maybe I should write it down. Okay, so let's go ahead and write down the answer. So later when you check the notes, you know. The converse is if the square of a real number x is greater than 4, then x is greater than 2. Now, what about the inverse?
If a real number is not greater than 2, then its square is not greater than 4.
Yes. So if a real number is not greater than 2, and then its square is not. So we negate both of them. It's not greater than 4. All right, now next, what about, but by the way, this doesn't change. It's a little different from really doing negation of that part, because when we do negation, we have to change it for any to there exist, but this one is still for any. When you do inverse, you don't have to change that part. It still works, that the inverse will still be any real number. For any real number, if it's not greater than 2, then its square is not going to be greater than 4. Now, contrapositive. And that would be doing both, right? So if the square, I can do converse first and negate the converse. We got to do both of them. So if the square of any real number, x, is not greater than 4, then x is not greater than 2. All right. So that would be the section 2.2. Now we're doing all of this because later when we do the proof problems, we have something called an indirect proof. When you cannot prove the problem directly, you try to do it indirectly. The first thing you're going to do is to negate whatever they want you to prove. So you got to do negation of any kind of statements. Now let's look at 2.3. All right. Statements containing multiple modifiers. So far, the examples in 2.1 to 2.2. In one statement, we only have for any, or we only have there exists. What if we have a statement that has both of them? For any, there exists, or there exists for any. So there will be two possibilities here. It might have a little bit of confusion here. These two, when you change the order, they are different. So I'm going to give you a kind of like a real life example. Okay, so let's say, let me write down this. I guess I'm just going to go ahead and use the symbolic form. There exists a key. I'm going to call it X, such that X opens X opens I'm going to change it to the order I want it. So such that for any door Y, X opens Y. In real life, you probably won't say the sentence this way. This is the reason I put it this way is because I try to get to the format we usually use in math. So in the other word, what does this sentence mean? It says there is a key that can open all doors, every single door, right? For any means every door. Okay, so that's what it means. Well, I guess in real life we do have keys like that, right? So you have maybe what we call a universal key or something that can open every single door. I think we do have a key like that because sometimes when I left my key in my office, I just go to the faculty office and ask them to open the door for me, and then they have a key that can open every single office door. So there exists a key such that for any door Y open X, the key X opens the door Y. Well, look at this statement. It has two quantifiers in here. There exists for any. Okay. Well, what if we switch them? Does it mean the same thing or not? If I switch them, I change this to, it's not doing negation yet. Okay, we're not doing negation yet. I would save maybe a little bit of space. So I want to kind of explain a little bit more when we can tell that. If I change there exists to for any key X, there exists a door Y. Oh, I should have it backwards. Maybe this won't be a very good example. I have to kind of switch then. Move this. Sorry, I moved the whole thing, not just that. So for any door Y, there exists a key X such that X opens Y. All right, so switch for any door Y and there exists a key X. For any door Y, there exists a key X such that X opens Y. The second sentence is like saying, any door here, I have a key that can open that door. So think about these two sentences. Do they mean the same thing or different things? Are they equivalent? The first statement says, I have a key. There exists means I have one. Okay, I have a key that can open every single door. The second statement says, any door, I have a key that can open that door. Does that mean the same thing or different things?
Means the same thing.
Means the same thing? Not exactly. Okay, so that's the confusion part. Confusing part here because a lot of times we think they're the same thing, but they are not. So that's why I need to save a little bit of space here so I can explain a little bit more. So when we have this question, how many keys are there? Just one key. Okay, so one key, we call this key X. How many doors are there? For any door, how many doors are there? Usually many, right? Maybe infinite many, maybe like 10 doors. So I'm going to use different variables to describe it. So we may have door Y1, door Y2, door Y3. So we may have like 10 doors, Y10 or 20 doors. But this one key X opens every single door, 10 of them or 100 of them. Okay, so notice that one key. But look at the second one. Because we change the order. For every door, how many doors do we have? Every door. Many, right? Okay, all doors or many doors. So we still have Y1, Y2, Y3, Y4. So maybe let's just say we have 10 doors. It says there exists a key X. How many keys are there? One key? Every door, I have a key. Every door, there's a key. That's what happens in real life, right? Every door has a key. Is this key a one key?
Same amount of keys as there are doors.
You could say that.
One key per
Okay.
door.
That's right. Both what you said, you combining the two answers, that would be right. So there are two possibilities. One of them could be every single door, there is a key. That's why usually when we have in normal life, right? Because if everybody has the same key, well, you can go to anybody's house now, right? So normally, for each different door, you have a different key. So door Y1, you have a key X1. Door Y2, you're going to have a key X2. Door Y3, you're going to have a key X3. Normally, they're different. And for each one, you're going to have a key, right? But it's possible somebody has a key, just one key that opens all these 10 doors. It is possible, but it doesn't have to be that way anymore. In the first case, you can only have one key. You're not allowed to have different keys because I have a key. When I say I have a key, there's one key that can open every single door. But the second case, when you switch them, I'm not saying I have one key. I'm saying for every door, so there is a door fixed. I can find a key. Another door, I can find a different key. Another door, I can find a different key. So you are allowed to use different keys. Well, you are also allowed to use one key. That works. But these values could be the same or could be different. Could be different or the same. Could be the one key or the same. Okay. All right. So that's the difference here. And I'll give you another real life example. Any disease, there is a cure. So does this cure have to be the same cure? Like maybe let's say medicine. Any disease, there's a medicine for that. This medicine doesn't have to be the same medicine, right? Okay. So if you have for any disease, instead of doors, and you may have many different medicine you have. So you could have medicine 1, medicine 2, medicine 3, and many different, any disease. You could have disease 1, disease 2. Say, if you have stuffed nose, there's a medicine for that. If you get a lung disease, there's a medicine for that. Then if you have heart attack, there's a medicine for that. If you have high blood pressure, you have different medicine there. In real life, I don't think we have medicine that's for everything, right? For the doors, yes, we could have a key that opens every single one. But for diseases, so I don't think we have one that can cure all the diseases. So in that case, all of the medicines will be different, right? Some of them may be, I don't know if there are any two diseases, maybe you can take the same medicine, possibly. But the thing is, they don't have to be the same. They could be different. All right. Similarly, when I say change the order, there is a medicine that is for every disease. That the medicine has to be fixed, right? So if I change the order, switch them, there is a medicine, whatever that medicine is, that cures every different type of disease. So far, I don't think we have anything for that, and as you can see, that's the difference here. Okay. All right. Any question? So now, is that clear, the difference? Okay. So now we're going to look at example. Math example, math questions, kind of like this. When we change the order, it changes the x. There exists, when they say there exists first, this x has to be fixed. It cannot be different ones. But if you say for any first, this x can be different x's. They don't have to be the same. It could be the same one, but they don't have to. So the example we're going to look at is there exists a y and z such that x plus y equals 1. Okay, that's the first question. I'm going to go ahead and write down the second question. There exists x in z. Save a little bit space for the answers such that any y E. X plus y equals -1. All right, look at the first, these two problems, when you look at them for any that exists. That exists and then for any. So as you can see, the order is different. For any, whenever you see the symbol for any, it means there are many, many of them. So for any y here, there are many, many of them. So you could have different values for x. So in this case, for any x in D, D is this number set right here. So what kind of values x can take? What values x can take? -2, -1, 0, and 1, 2, right? So this x could be negative. Let me just make a table maybe, so I don't have to write down x1, x2. For x values, it could be -2, -1, 0, 1, 2. For any number in there, that's different values for x. Just like any door, you may have many, many doors. There exists a y in E. So this y value can change based on that x value. So can we find a y value such that x plus y is equal to 1? So in the first case, if x equal to -2, we want this, x plus y equals 1. X plus y equals 1. So -2 plus one number will be equal to 1. What kind of number for y?
3.
3, right? So y has to be 3 here, but is 3 in E? Is 3 in E? Is 3 a number in this number set? No, unfortunately, no. So you cannot find a number in the number set to satisfy this conclusion, x plus y equals 1. Although all the others you can check, you can, but this one you can't. And you can really stop right here, say this is false. Why is this false? Because for x, if x equals -2, this y, such y does not exist. Does not exist. I'm just going to put a D and E here. Does not exist. So that means this statement is false. It's kind of like there's a door X. You cannot find a key for that door, and then the key you have, a bundle of keys you have. So this is like the keys you have. None of them can open that door. So that would be false. Maybe there's another 3 does exist, but it's not in the keys you have. So 3 is outside the number set. Now let's do the second one. There exists a x. This x has to be fixed. We don't have many different options. So whatever that x we're looking for, we don't know yet. Let's check y. This y has for any, that means y can change. And y can take -2, -1, 0, 1, 2. Such that x plus y equals -y. In the first case, y is -2 equals 2. Okay, so can we find a number, whatever the x is plus -2 equals 2, can we find a number for that? What number would that be? Would be 4, right? Okay. But for the second case, that's a potential answer for x. For the second case, what does x have to be? 2. Well, we have to have different x for that. Well, in this case, you're not allowed to use different because they said x first. You have to have one x value that works for every single one. Well, so you're going to say this is false. This x does not exist. Such x does not exist.
Your meeting has ended.